Okay, in this video we are going to talk about some things that my calculus students are still kind of struggling with a little bit with 1 week to go before the AP exam. I think a lot of people will find this very helpful. Let's dig in. Okay, the first concept is definitely some summation things. So what we want to look at is the limit of a Riemann sum for a definite integral. So the limit as n approaches infinity, the sum from k equals 1 to n, f of x sub k delta x is, kind of by definition, the integral from a to b of f of x dx. Now, in this formula, delta x is b minus a divided by n, and x sub k is a, where you're starting your integral, plus k times delta x. Crucially, when you're doing these problems, x sub 0 is equal to a, and x sub n is equal to b. So we're going to use that a lot to figure out the bounds of the integral. Let's look at a problem. So a definite integral equivalent to is, so this would be like a multiple choice question. I just took away the answers because I didn't have time to make the answers. Step 1 is we want to identify delta x. So 3 over n is definitely our delta x. Just like look at the form of this thing. We have like something being plugged into something times this additional quantity. That's going to be your delta x. So we know delta x is 3 over n. Now from there, looking at the form, we can figure out what x sub k is. I think x sub k is 5 plus 3k over n, so I'm going to write that down. Then, once we have x sub k, we want to immediately find x sub 0, so plug in 0 for k, and you get 5 plus 0. And then x sub n, plug in n for k, you get 5 plus 3n over n, which is 5 plus 3, which is 8. Then we need to figure out what are we plugging x sub k into. Just look at the form of this thing, and you can see that you're doing your x sub k value squared. So I think our function is f of x equals x squared, and from there we can write our definite integral. So it's the integral from 5 to 8 of x squared dx. I also probably should have mentioned at the very beginning, I'm getting new siding on my house. You might hear a lot of hammering during the process of making this video. Sorry about that. All right, another thing that involves kind of summations and limits and whatever, you can write out that summation, and sometimes in multiple choice questions they will do that. They'll give you like the left side of this and ask you what the right hand side looks like. So the limit as n approaches infinity of delta x times this giant quantity f of x1 plus f of x2 plus dot dot dot, that's basically a right Riemann sum. It kind of doesn't matter if it's a right or a left Riemann sum actually, and maybe I'll say a word about that at the end. But that limit is the integral from x0 where you're starting to xn where you're ending, or from a to b of f of x dx. So again, it comes down to like looking at the form and figuring out what's going on. I think pretty much always they put delta x at the beginning of this, unless it's like a trick question, which I don't think they really go for on the AP exam, where sometimes like you'll have 5 times delta x, so you have to factor out a 5 and it's in front of your integral. But let's say delta x is this, and then we look and we say like, what could we make x sub k? Well, we have just like all these things. We have 1 over a thing, 1 over a thing, 1 over a thing. So I think x sub k looks like it would be 1 plus 8k over n. And if this is a right Riemann sum, we always start out by like looking at x1. And if you plug in 1, you get 1 over 8. No, 1 plus 8 over n. If you plug in 2, you get 1 plus 2 times 8 over n, etc. So I think that's a good choice. From there, we always find x0 and xn. Like always, just remember that's what you're doing and it makes it a lot easier. So x0 is definitely 1, and then xn is 1 plus 8n over n. 1 plus 8 is 9. So we have the bounds of our integral. Then we have to ask ourselves, well, what are we plugging into? So it's 1 over a thing, 1 over a thing. I think our function is definitely just 1 over a thing, so 1 over x. We can write our integral, and this problem says to evaluate it as well. I don't know, on a multiple choice question, you might have to choose the integral, you might have to evaluate the integral. So our integral will go from 1 to 9, 1 over x dx. The antiderivative of 1 over x is the natural log of the absolute value of x. It's really important that you include that. I just did all the fundamental theorem part. The absolute value really needs to be there. Sometimes they give you negative bounds for this, and you're like, oh, is that even possible? It sure is, because when you do the natural log of the absolute value of x, if you plug in a negative, the absolute value just takes care of it. So don't forget those absolute values. But this is just another example of something that might come up. Certainly multiple choice. You would never see this, I'm going to say. You will never see this on a free response question. Another thing that I actually think is like maybe the easiest one, but it's unfamiliar when you see it. So if the sum from 1 to n of f of x sub k delta x is equal to s of n, just some function of n, that means that what they've done is like they wrote a Riemann sum and then they worked it out using all the kinds of formulas that you can use for summations that aren't really a part of this course, and they just work out what it is equal to. Then the integral from a to b of f of x dx is just the limit as n approaches infinity of that thing they give you. So we just have to take the limit of s of n. So here's an example problem. The sum from 1 to n of our thing is equal to 4n quantity 2n plus 3 quantity 2n plus 1 all over 5n cubed. We want to know what the integral from a to b of f of x dx is. Well, we don't even need to know what a and b are to do this, because all we have to do is take the limit of that summation, right? That's the definition of a definite integral. So we want the limit as n approaches infinity of all that. When I look at this, I mean, you can like expand it and use L'Hopital's, but since you're going to infinity, you can just use like orders of magnitude on this thing. The numerator is basically 4n times 2n times 2n, which I think is 16n cubed. So as you go to infinity, that 16n cubed really dominates the numerator. The rest of it kind of falls off. So it's basically just 16n cubed over 5n cubed, which is going to give you 16 over 5. That's totally acceptable way to think about that when you're doing multiple choice. If you're doing free response, first of all, I don't think you would be on this question, but you'd want to use L'Hopital's rule on that like a lot, and or divide through by the highest power of n in the denominator, which is actually a little bit easier on this one than using L'Hopital's. But we'll go with 16 over 5 on that. It's the concept that really matters. I think you might see this on a multiple choice style of question. A random handwritten question that I'm going to add in here, unrelated, kind of a new topic. Let's say we have this table of values. We have x is 12, 14, 16, 18, 20. F of x is 10, 25, 27, and 10. We're told that f is continuous and has exactly 2 critical points. Exactly 2 critical points in the interval from 12 to 20. Which of the following is true? So f of x is greater than 0 for all x on the interval. F prime exists for all x on the interval. F prime is greater than 0 for all x. Now notice this, it's not on the interval. It's just between 12 and 14. And then f prime of 20 does not equal 0. We want to figure out which one is true for this. Now, the first thing that I notice is right away, it says the function is continuous. It does not say that the function is differentiable. So we don't want to assume differentiability. That's one of the biggest mistakes that I see people make, is they just like, I don't know, people just assume everything is differentiable, and that's just not true. So when you see something is continuous, you should basically assume it's not differentiable. Think of the absolute value of x. If you see something is differentiable, then that implies that it is continuous, and you're good. So what I would do is a scatter plot, I think. So, just let's do it quickly. Just get them in the correct relative positions. You don't need to go crazy on this. So like 12 and 20 should both have the same height, and then you want to go way up and then less up, and then you want to be below 10. So we have something like this. Now let's investigate each one kind of individually, right? So f of x is greater than 0 for all x between 12 and 20. I think what they want you to do here is make assumptions, right? So what I'm going to do is just sketch a graph that I think doesn't contradict anything that we're given, but also shows that this thing doesn't need to be true, right? So we've got all of those points. Our function is continuous. Our function, as I've drawn it, has exactly 2 critical points. It has that like maximum and then that minimum somewhere between 16 and 18. So it's good. So this is not true. F prime exists for all x between 12 and 20. This, I think you can just, f is not differentiable, or is not given to be differentiable. It could be, but we don't really know. You could cross this out right away. But also, I think it's helpful to like try to sketch a graph. What I'm going to do, because it makes the most sense to me in my mind, is I'm just going to cause that minimum there to be like a sharp turn, which would be a valid reason on a free response question to say that a graph is not differentiable. Sharp turn or a corner. So we're not differentiable at that minimum. You don't need f prime to exist everywhere. Let's get rid of it. F prime is greater than 0 for all x between 12 and 14. Now you can see every graph that I've drawn so far does suggest that that's true, but does it need to be? Like, couldn't I make the maximum be somewhere between 12 and 14 and then just kind of like go through the points? So let me sketch that in. So we have this. We're not breaking any rules. We still have just 2 critical points. This does not need to be true. And so finally, our answer just has to be D. And I would argue that the reason that it kind of like has f prime of 20, that definitely should not say 20. Oh, that's supposed to say f prime of 16 does not equal 0. It's supposed to be the one in the middle. I apologize for that. This problem should have said f prime of 16 does not equal 0. I mean, f prime of 20 also does not equal 0, but f prime of 16 does not equal 0. We know that it can't equal 0 because we're going to have a relative maximum. We're going to have a relative minimum. At both of those, we'll get critical points. And the value at 16 can't be the maximum or the minimum because there's a point above it and there's a point way below it. So those have to be our max and mins. There's no way that D is the answer to this question. So I apologize that I wrote that wrong, but it can't be the answer anyway. That literally could have said anything and it would have to be the answer. So 3 things I think come from this. One is don't confuse continuous with differentiable. That's actually probably the biggest one. You should always be checking what you're given. Like, are you given twice differentiable? If a function is twice differentiable, that means that the function is differentiable and f prime is differentiable. The important thing there is if a function is differentiable, the function is continuous. If f prime is differentiable, then f prime is continuous. And if f is twice differentiable, we kind of don't know much at all about f double prime. So just kind of keep that in mind. The other thing I would say is draw graphs, don't just think about them. Like, you waste a lot of time thinking and you'll forget what you have already thought about or what you haven't thought about. Just draw your graphs. And then the other thing is always try to draw multiple graphs that satisfy the given information so that you make sure that you're not like bringing into the problem like something that's not really given in the problem. So I think those 3 things are all illustrated really well by this problem. And also that should have said f prime of 16. All right, the next concept that I want to talk about is just like generally slope fields. Slope fields are not bad. I have multiple videos that cover slope fields. I really recommend that you check those out. One of them is about matching slope fields to their functions. It's like 2 separate videos. I go through a ton of them. It's worth your time to check out now. I don't know if you're like cramming at the last second, maybe not. So first, I'm just going to do a bunch of problems. Slope field for the differential equation dy dx is given. The slope field corresponds to which of the following differential equations? So in this particular problem, the technique that I would use is, I think I can draw a solution curve. So in that case, I would draw something like this, and then I would just ask myself, what does that look like? I think that kind of looks like negative cosine, which means that's what y is equal to. So the differential equation should just be the derivative of that thing. The derivative of negative cosine is positive sine. And so I think from there, we can just select our answer. So if you can sketch a solution curve, you should try to sketch it because it gives you a lot of ideas about what the differential equation is. And then if you can guess what the equation is for the solution curve, you can just take its derivative and that tells you the differential equation. So sometimes that won't work, but frequently it will. The next problem. Slope field for the differential equation is given above. The slope field corresponds. It's the same problem. So the first thing that I do when I look at a slope field is I try to find where the slopes are 0. So I see here, the slopes are just 0 when y is 0. Every time y is 0, the slope should always be 0. I look at the differential equations and I see one of them has an x in it. And that means that if x changes, like y can be 0, but if x is 1, dy dx would be positive 1. And we know that everywhere y is 0, the slope is 0. So anything that has an x involved in it is out at this point, which means I actually could have crossed out e to the negative x, but I didn't cross it out yet because I want to cross that out for a different reason. But we could have crossed that out there as well. The next thing that we want to look at, I think, is what's going on with these slopes, right? So if y is positive, the slope is always negative, and if y is negative, the slope is always positive. So let's just investigate. So for this next one, if y is less than 0, using dy dx as y squared, we're always going to get positive. It doesn't matter if y is positive or negative. We would always just get positive slopes, but you can see there are places where there are negative slopes, namely if y is positive. So we're going to cross this one out. We can do basically the same thing for the next one. If y is less than 0, then you have like negative 5. The opposite of negative 5 is positive 5. If y is less than 0, we get positive slopes. If y is greater than 0, we get negative slopes. I think this is the answer. So I'm going to choose that as my answer. But I really, if I didn't already know that I can exclude D, I would have to think more about D as well. D, I think they're trying to fool you into choosing it because the solution curves themselves look like e to the negative x. And so people kind of want to say like, oh, that's it. You're not finding the equation of the solution curve. You're finding the derivative of the equation of the solution curve. So the reason that I want to knock out d just to like demonstrate the technique on this one is I want to say that along vertical lines, the slope wouldn't change. Okay, so I'm saying this backwards here. Looking at dy dx as e to the negative x, there is no y in that differential equation, right? Meaning if you move up or down, the slope should not change. So if we look at our slope field, moving up and down, the slope does change, right? When y is equal to 3, we get a different slope than when y is 0, and we get a different slope when y is negative 3. So since the slope is changing when y changes, there should be a y in your differential equation. You can cross out d. You also could have crossed out d on like the very first thing that we did, but we didn't. And so that's a good problem. Let's look at the next one. The slope field for the differential equation is given in the figure, which the following statements are true. Okay, so again, I like to look at my slope field and just figure out where my horizontal lines are. One of the key things about any horizontal line that shows up in a slope field, actually basically anything linear that shows up in a slope field, you just cannot cross them. So if you have like a slanted line, like y equals mx plus b, going through your slope field, you're never going to cross that line. It's going to end up an asymptote for your solutions. And the same thing is happening here. So the first item that we're given, a solution curve that contains the point 0, 2 also contains the point negative 2, 0. Now, I think the fact that y equals 1 is a horizontal line passing through this is going to mess that up, right? If we do a solution curve there, you can't get past y equals 1, so you can't get down to negative 2, 0. This is out. Based on having just like drawn our solution curve, we could put in another one that's kind of like decreasing and concave down. Yeah, as the y values approach 1, the rate of change of y, the slope of the solution curve, does approach 0. 2 is definitely correct. Okay, all solution curves for the differential equation have the same slope for a given y value. We can just look at the slope field and we can see that that is definitely true, right? So, I mean, that is our answer. Now, one thing to think about is if the y value is determining the slope, that means that the x value has nothing to do with the slope. Our differential equation will only have y's in it. There will not be any x's in our differential equation, because if x was in the differential equation, then changing x would change the slope, and that does not happen. All right, let's take a look at the next question. Oh, there's our answer. Slope field for the differential equation is given, so it's y squared, quantity 4 minus y squared. So there's like a lot of horizontal tangent line, horizontal solutions to this, I guess. For example, y equals 0, y equals 2, y equals negative 2 will all make dy dx equals 0. I love to sketch those in. I think they're really helpful. We cannot cross those. That's one of the main things to keep in mind when you're looking at these. So let y equals f of x, the particular solution through negative 3, negative 1.5. What is this? The value of the limit as x approaches negative infinity of f of x. So let's just sketch it. If we start down here, we are actually trapped between two of these horizontal lines, right? If you go to infinity, you're going to approach y equals 0. If you go to negative infinity, you're going to approach y equals negative 2. And that's just the answer to the question. So I don't think slope fields are all that bad, but you do have to like keep in mind what you're doing. I do recommend that you watch the video of matching slope fields to their differential equations. It can grab you a point or two on the exam. Let's take a look at the next concept. So there's actually two concepts here that I want to dig into, and I talked about them last week, and I probably will talk about them every year for the rest of my career before the AP exam. The first one is there's this universal belief in natural logs showing up when you're doing antiderivatives. That is not the case. They don't need to show up. Every time you separate and integrate, you're not guaranteed to get a natural log. And then the other thing is the question of when to solve for C. So I've made a little thing in Canva for this. So you should solve for C ASAP. If you need to exponentiate, then you should wait. You should say that to yourself a couple of times. Is it a poem? I don't think so. But is this nice looking? Sort of. I don't know. Could have done more with the font. Let's take a look at some problems. So please stop thinking you always get natural log when separating. That is my plea here. So I've written 3 differential equations. I'm not going to show you all the work, but I'm going to basically do it. So first, you separate. The first one, the y squared, goes up into the numerator on the left, right? The second one, the y squared, ends up in the denominator when you divide both sides by y squared. The third one, the y ends up in the denominator when you divide both sides by y. The key difference between the second and third one is in the second one, you have y squared in the denominator, which is really just y to the negative second in the numerator. So we're going to do plus 1 times the reciprocal. In the third one, we have 1 over y, which is famously the derivative of natural log. So now I'm just going to do all the antiderivatives. I didn't really check my work on this, but I'm pretty sure that I'm right. So we get 1/3 y cubed equals, integrate on the right. We get negative 1 over y. We get negative y to the negative first, right? Because you have y to the negative second plus 1 times the reciprocal. We get this. No natural logs have shown up. And then on the last one, we have the natural log. The absolute value of y is sine of x plus c. Okay, so now the question becomes, when do I solve for c? Solve for c as soon as possible if you don't have to exponentiate. So I have written down, you should solve for c now on the first one, now on the second one, and do one more step on the third one. So for the third one, we're going to exponentiate, which kind of changes a lot of stuff. You lose the natural log, you lose the absolute value, and the c becomes a coefficient. I have a lot of videos on that. Those are steps that I always skip, and I just jump to this. Y equals c e to the sine of x. Now you should solve for c. This is as soon as you should solve for c if you're going to exponentiate. It's kind of all I want to talk about on that one. Let's look at the next thing. Concept. Algebraic techniques that we just do not see often enough, so you could kind of forget that they exist. So I'm throwing this in. No one has really asked about it because we don't see it often enough. It's probably on the exam. I bet one of these will be on a multiple choice question. I could imagine a universe in which there's a strange FRQ where this is maybe like one part of it. So one of them is divide and integrate. And then the second one is complete the square and integrate. So you're going to divide and integrate when the degree of the numerator is greater than or equal to the degree of the denominator. These are things you do on rational functions. So polynomial divided by a polynomial. And then complete the square and integrate. You're going to do that when you have a quadratic in the denominator and u substitution just doesn't work. So let's take a look. So first one, we have the integral of 2x squared plus 5x plus 5 over x plus 2. The degree of the numerator is greater than the degree of the denominator. That means you have to divide. I'm going to do long division. You could do synthetic division on this. I honestly think on the exam you would probably always be able to do synthetic, but I think that long division is safer. So here's all my work. I get 2x plus 1, remainder of 3. So I can rewrite my integral as the integral of 2x plus 1 plus 3 over x plus 2. And then we just integrate it, right? You're going to get a lot of natural logs when you integrate, when you divide and then integrate. It's kind of like that happens almost all the time. So the degree of the numerator greater than or equal to degree of the denominator, divide and integrate. The next one, you look at it and you're like, maybe if I just let u equal the denominator, but then you have a problem because you would need 2x minus 4. There's no way to get that 2x, right? You could get the minus 4 if you needed to, but you can't multiply in an x. This, because we have a quadratic in the denominator, is your sign to complete the square. So what I would do is I would like separate it out and make it x squared minus 4x. I leave a space. I put the 5 all the way at the end. You take the coefficient of x, which is negative 4. You divide it by 2. That's negative 2. You square it. That's 4. You're going to add it and subtract it. Also, you might just say to yourself, x squared minus 4x like should have just a plus 4 at the end there, and you can break 5 into 4 plus 1. That works. But completing the square, algebra 1 technique, go watch some videos. Then at this point, we get basically just x minus 2 squared, and then we get plus 1. And so what happens is you always get the first 3 things are a perfect square. The last one is either 1 or you have to like divide by it because for arctan you really need that 1 there. So our answer here is 3 arctan of x minus 2 plus c. So this, if you have a quadratic in the denominator and u substitution, you should always just try to make u equal the denominator. If that fails to work, you should try to complete the square, and then you should be on the lookout for an arctangent in your answer. For Calc BC, there's another algebraic technique that you need, which is partial fractions. That's guaranteed to be on the BC exam, but it also comes up a lot. And so you're probably way less out of practice if you're taking the BC exam for that concept. So, I'm not going to go over it right now. All right, the next concept, some horizontal asymptote stuff, which I don't know, is this really calculus? I guess it is really calculus, but don't overthink these. I think that an Algebra 2 student who's really on their game could probably figure out these sorts of things. So which of the following has a horizontal asymptote at y equals 0? So I'm going to look at these and just think like relative growth rates. X to the 100 grows so much faster than natural log of x that it just has to go to 0 overall. That f of x right there has to go to 0 as you approach infinity. So the limit as x approaches infinity of natural log of x over x to the 100 is definitely 0. If you're not sure, you can actually just use L'Hopital's once on this. And when you do it, you get 1 over x over 100x to the 99th. And then when you simplify that, you end up with the limit as x approaches infinity of 1 over 100x to the 100. Clearly that goes to 0. So this is definitely one of our answers. The next one, I'm not even going to do work. Exponentials are well known for growing fast. Logs are well known for not growing fast. So this race is just going to be out of control. E to the x is going to win. That definitely goes to infinity. There's no way. For the third one, I'm also going to say e to the x will beat any polynomial. It just takes time. So this limit is definitely 0. If you wanted to, you could just keep using L'Hopital's over and over. The denominator is never going away. The derivative of e to the x is e to the x. In the numerator, you're going to get like 100 and then to the 99th, and then 100 times 99 to the 98th, 199, 98 to the 97th, etc. You keep going. Eventually, the derivative of x to the 100 is going to go to 0, and then you just have 0. So you can think it through, but also exponentials are just going to win. It's called relative growth rates. There's no way that that's not going to win. So I would say that 1 and 3 are our answers here. So some people struggled with that. I think people wanted to do more work, or maybe they were just intimidated by the amount of work they thought it would be if they did it. It's hard to know. Another question that I thought of, so I just hand wrote it in. Find the horizontal asymptotes of f of x equals 1 over 1 plus e to the x. People routinely screw this up, basically because rational functions have warped our brains into thinking that the limit to infinity and negative infinity are always going to be the same. But that's just not true. That's only true for rational functions if you get a finite number. So let's look at this. Step 1, we got to go to infinity for this. This you could do L'Hopital's once if you want. This isn't even L'Hopital's. This is just 1 divided by infinity. That's definitely 0. So y equals 0 is a horizontal asymptote. Now, we also, because it's not a rational function, we need to go to negative infinity. The way that I like to deal with this is I just think of the graph of e to the x. If you go to negative infinity, e to the x definitely goes to 0. So when you take this limit to negative infinity, the ones don't have x's. They just stay. So you get 1 over 1 plus 0, which is 1. So we're getting y equals 1. So this has 2 different horizontal asymptotes. You really got to look out for that. Also, this function has no vertical asymptotes because 1 plus e to the x has a horizontal asymptote at 0, and you're moving it up by 1, right? So you're never going to have a vertical asymptote there. On the other hand, if you had 1 minus e to the x, that does have a 0, so you do get a vertical asymptote. So just be on the lookout for those sorts of things. But crucially, non-rational functions can have 2 horizontal asymptotes. I don't know if you noticed, but I started saying crucially like the other day, and I just cannot stop it. So hopefully I get that verbal tick out eventually. Let's look at another one. So I didn't type this up because it's super annoying to type this. This type of limit causes people problems every year, all the time, for life. So we have f of x, which is this crazy function where the limit definitely does not exist at x equals 5. We also have, but the limit as x approaches 5 from the left of f of x is definitely 4, and 5 from the right of f of x is definitely negative 2. That's going to be important. G of x is almost our familiar function, right? The absolute value of x over x, but things have happened to it. We shifted it 3 units to the left, and then we moved it up half a unit and then multiplied by 2. Doesn't really matter. I think multiplied by 1.5 probably. It doesn't matter. We don't need that. We just need the graph. The question we're trying to answer is, obviously the limit as x approaches 5 of f of x does not exist. The limit as x approaches negative 3 of g of x does not exist. For some reason, we're being asked about the limit as x approaches 5 of f of x times g of x minus 8. So we're going to take the graph of g and we're going to shift it 8 units to the right. And something really nice happens when you do that. So what I would do is I would actually redraw this. I'm not a fan generally of redrawing graphs when we do transformations. I prefer to deal with them with u substitutions. But in this case, because there's multiple functions involved and it's an easy graph to shift, I just shifted the whole thing 8 units to the right. which takes that point that was at -3, that jump discontinuity, and moves it now so it's at 5. This is good. It means that we have a chance. So now we're gonna break this down into a limit from the left and a limit from the right. So the limit from the left is going to be, look on the graph of f and approach from the left, we definitely get 4. On the graph of g of x minus 8, as we approach 5 from the left, we definitely get -1. So we get 4 times -1, -4. Now we're going to do the same thing from the right. So f of x from the right, we definitely get -2. G of x, as x approaches 5 from the right, we definitely get +2. And -2 times +2 is -4, which means this limit does exist. So we have two limits that on their own don't exist, but then the product does exist. It's not a contradiction. All of the limit rules only apply if both limits exist, right? The limit of a product is the product of the limits, provided both limits exist. If they don't both exist, you have to do more work, and this is the work that you would have to do. All right, so that one like murders people every year. It's a shame. The last thing that I want to talk about, I'm not actually going to do any problems with it, but I've noticed, and it's like a perennial thing, you got to know your cross-sections for volumes by cross-sections. So first off, if we have a graph like this, top, takeaway, bottom, it's set up basically, if it feels like you would be comfortable finding the area, it's probably a dx problem. You're told that the cross-sections perpendicular to the x-axis are whatever. That means automatically you're going to use dx. When you calculate s, I always call it s for like the segment that's involved. All the area formulas are in terms of the segment. So s is going to be top, takeaway, bottom. You're always doing top, takeaway, bottom when you're dealing with dx. And then our bounds, we have like an x value that we're starting at and an x value we're ending at. It's like the left and the right. So our bounds are just going to go from A to B. And now this is the important thing. You want to look it over at the end. It doesn't matter so much for x because people don't screw it up as often. We got dx, we have x, and then our function should be functions of x. That's a good thing to think about because for dy, people screw it up all the time. So here's a graph. You're told that the cross-sections perpendicular to the y-axis are squares or equilateral triangles or whatever, right? So you set it up, you draw in your little horizontal segment for s. Because you're perpendicular to the y-axis, you're going to use dy. And anytime you're not sure, just think, what would I do for dx? Like, what am I doing for dx? Perpendicular to the x-axis, I use dx. So perpendicular to the y, I have to use dy. Then when you calculate s, you always want to get a positive, so you got to do the big thing minus the little thing. You're always doing the right-hand curve minus the left-hand curve. And then we need our bounds. Since everything here involves y, we want to go from the lower y value to the upper y value. So our bounds are going to be from c to d. And then you look this over and compare it to the x version, and you notice, dy, y bounds, and then we need our functions to be functions of y. After you set that up, you just have to memorize these, or at least I recommend that you memorize them. So we have different shapes. So one of them is a square. That's just s squared. That's the easiest one. It's also the one they ask about, like definitely the most frequently on the free response. The next most frequent on the free response, I actually think is the generic function. And then after that, I think is a rectangle. And then it's really uncommon to run into semicircles or equilateral triangles. But in the multiple choice, you could run into any of those. So square is s squared. Equilateral triangle is √3/4 s squared. Semicircle is the one that it's the most important to memorize because it's the hardest one to derive. That's pi/8 s squared. A rectangle, they will describe it to you. They'll be like, oh, the height is like 5 times the base, and the base is in the plane. So the height is 5 times s, the base is s, so you get 5 times s squared. That's kind of like what happens almost all the time. It's also an option that they'll just say the height is 12, and then the base is just s. So then the area function just becomes 12s if I said 12 before, which I think I did. So also be on the lookout for that, but like more generally, this is kind of what usually happens. The generic version, they're just going to explain it to you. They're going to be like, cross-sections perpendicular to the x-axis have an area of, 15x squared plus 35. And you're like, why is that the area? But it doesn't matter. No matter what the area of a cross-section is, you just integrate that to get the volume. So our sort of like, I actually think it is the easiest. because they're going to give it to you. You don't have to work anything out. And it's like an excuse for them to see if you know how to do it, and if you know how to do like a weird integral or something. So like in Calc BC, for example, it might be an integration by parts type of thing. In Calc AB, it would probably just be something that doesn't naturally arise, like conveniently, like an x times cosine of x squared type of situation. I don't know, could be anything. But in general, the volume that we get when we have known cross sections is the integral from wherever you're starting to stopping, could be x values, could be y values, the area of a cross section. So you're just going to integrate the area of the cross section, d whatever. If it's perpendicular to the x-axis, it's x. If it's perpendicular to the y-axis, it's y. So that's a bunch of stuff that I wanted to kind of really highlight. We got 1 week to go. That's plenty of time to really work on some FRQs, find the things that you're bad at, get better at them. I think anybody who is not currently in a position to get a 5 can work really hard and get themselves at least 1 point higher in this amount of time. So I hope this was helpful, and good luck.